Okay, this is continuing topic 8.5, so this is part 2 of the 2 videos. So let's do a practice question. How to find the molarity of your unknown. So a 50 milliliter sample of HF, an aqueous solution of unknown concentration is titrated with 2.1 molar potassium hydroxide. The graph shows data taken during the titration. What is the concentration of the HF sample? So let's take a look at our information we're given. We've got 50 milliliters, so I like to draw just a little sketch of what's going on. I've got 50 milliliters of acid, my acid, HA, or we can now go ahead and write the formula HF. We do not know its molarity, so question mark molarity. It is titrated, so that means the chemical dropping into it is 2.1 molar KOH. And we've got our graph of our titration curve. So we want to know the concentration of our HF sample. So the best way to be able to do that is to be able to find where we have equal moles of our chemicals so that we can get moles of our acid. We've got the volume of the acid, we need its moles to be able to find that value. So we're going to use our graph to figure out how much base did we actually use, what volume of base did we use. So we're going to go to our graph and find our equivalence point, and I would estimate it about here. Since we have HF, that's a weak acid, so that's why we're starting at a higher pH. That's something to note on our graph here. So that's why our pH is shifted up, and I would estimate our pH probably to be around 9. Okay, so at pH of 9, our volume is that first line after 10, so our volume is 11 milliliters. So we've got 11, let's go ahead and add a 0 on that, milliliters of KOH of 2.1 molar KOH. Okay, now to solve this, we can use basically our dilution equation. You guys should remember from last semester, M1V1 equals M2V2. Some people also write it this way, V1M1 equals V2M2. Just so you can think you have to voom, VM. All right. So you can think about these 1s and 2s. Instead of being 1s and 2s, you can think about acid and base. So one side your acid, one side your base. So if I've got 11.0 milliliters and 2.1 molar, that's of my base. And that's going to be equal to my volume times my molarity of my acid. So my volume of my acid is 50 milliliters. And I don't know the molarity of my acid. Okay, why can we do this? Well, an acid and base reaction is 1-to-1. One hydrogen from our acid is joining with one hydroxide from our base to make our salt and water. So since they're a 1-to-1 ratio, we can use this dilution equation. The dilution equation has molarity times volume. Molarity times volume is moles. So this is saying the moles of my base equal the moles of my acid. And that's true only at the equivalence point. So that's why we use that point on the graph. So to solve, we would divide by our 50 milliliters. And we can leave these in milliliters because the units will cancel. As long as they're consistent, we're fine. So our molarity of our acid is going to be 11 times 2.1 divided by 50, which I got 0.462, and we've only got 2 sig figs, so 0.46 molar HF. All right, so that's how we can find the molarity of our unknown solution. This is the same type of calculation we can do at the regular titration. It's just that the way we're getting our volume of from our burette is from our titration curve. So instead of having to rely as much on us finding a color change with an indicator, we have a graph to help us. So it can be a little more exact depending on how good your graph is. Now, the other thing we want to find is the Ka. And again, this is that half of the equivalence point. So if our reaction happened our equivalence point was at 11. Half of that is 5.5. So we want to find 5.5 on our graph here, follow it up, so that would be here. So then I want to find the pH at that point and estimate it the best that we can. So I would say the pKa equals the pH when it is 4. I'd say that's about 4.8. Maybe 4.7 or 4.8. All right, so if I want the Ka, I'm going to do 10 to the negative pKa. So 10 to the negative 4.8. And I get, let's put that in scientific notation, 1.6 times 10 to the negative 5 is my equilibrium constant for my acid. And we can see that's a pretty common range for our weak acids there, HF. So that's how we can find our Ka value and our molarity of our acid, two really valuable tools to have for a reaction. So now we're going to take a look at how we do a problem, a titration problem, when we don't necessarily have the titration curve. How do we find the pH, the equivalence point, that sort of thing. So it says a student conducts an acid-base titration in an AP chemistry lab. They find 35 milliliters. So let's do some underlining here. 35 milliliters of 0.325 molar CH3NH2. So we can see that at CH3NH2, it's got that NH group. That's a really good indicator that that's our base. So we've got a volume and molarity of our base is required to titrate 0.265 molar HCl to the endpoint. Okay, so we've got a molarity of our HCl. We want to know the initial volume of that acid. We can tell that the HCl is our acid. It's one of our strong acids, so we don't have to worry about figuring out who's strong or who's the acid, who's the base. We know which one's strong. So first, we want to find the initial volume of the acid. We'll get to these other questions. So let's just call this question number 1. Okay, we want to know the volume of the acid. Well, we've got a volume and molarity of our base. We've got a molarity of our acid, so we can use our dilution equation. So boom, boom. And I'm just putting A and B to indicate acid and base, so we can keep track of our numbers. So our volume of our acid is what we want. Our molarity of our acid is 0.265 molar. Our volume of our base is 35.0 milliliters. And our molarity of our base is 0.325 molar. So if we want to solve for our volume, we're going to divide both sides by our 0.265. So 0.265. The molarities will cancel, so we're going to be left with milliliters. So we get 35 times 0.325 divided by 0.265. And we get 42.9 milliliters of our acid, which is HCl. So we know our initial volume of our acid. So we can use that equation to find initial volume, initial molarity, those kinds of things for our chemicals. All right, let's take a look at the second question up here. It says, how many moles of acid and base have reacted at the endpoint? Okay, well, if we want to find our moles of acid or our moles of base at that endpoint, then we just need to do a volume times a molarity. We can do it for either chemical. I tend to use the one I'm given both values for just because we have them, but you can use either one. So you could do, let's see, let's just use our base here. So if I want moles, that is equal to my volume times my molarity. Let's do it for our base. So that would just be that 35.0 times, we do need to put this one in liters if we're going to do that. So 0.035 liters, because liters times molarity gives us moles. So that would give us 0.035 times 0.325, and that would be equal to 0.0114 moles. And that could be moles of our acid or moles of our base, because remember, they're equivalent, they're equal to each other at the equivalence point. So how many moles of acid base have reacted at the end point or equivalence point? They should be equal. So that is our number of moles of acid or base. Okay. So now there is a third question. Determine the pH of the solution at the end point. And this is the part that's a little harder. We're going to do that on a new slide. So let me go to my new slide, just so we have space here. And I have an explanation of what we're going to do, because this is where it can get a little trickier. Okay. So it says, so we're doing this part that's underlined, determine the pH of the solution at the end point. So if we did this titration and we didn't do a titration curve, this is what we would have to do to find that pH. Now, the reason we have to do this process is because it is a weak acid a weak base and a strong acid, and we have equal moles of them. So we have to do a little bit of a weird process. So to determine the pH, we need to think about the reaction occurring. The weak base has been neutralized at the endpoint by the strong acid. Therefore, there is no strong acid or weak base left in the solution. They're gone. They're used up. However, the reaction produces the conjugate of the weak base. So when our base reacts, we can see that here, it produces its conjugate where we've added that hydrogen ion. Now, that chemical, the conjugate of a weak base or the conjugate of a weak acid, this causes a secondary reaction with the water that's present for these aqueous solutions. And that secondary reaction is going to affect our pH, affect our equilibrium. So we can determine the effect of this on the equilibrium by determining the equilibrium occurring between the conjugate and water. Then pH can be determined. So we can see our reaction there, our normal reaction that took place. And when this reaction occurs, we create that conjugate, so CH3NH3+. So I'm going to take that, and we're going to explore what that chemical does when it's added to water. Okay, because it's hanging out in that aqueous solution. So what happens there? Well, this CH3NH3+, when added to water, that water can grab that extra hydrogen that this thing has, and it's going to create CH3NH2. And when water grabs an extra hydrogen, we get H3O+. Remember, H3O+ is just like our hydrogen ion, but with water. So it kind of breaks it back down and releases some of that hydrogen ion back into the water. So we have a rice table set up. Now, water is always your liquid. We can ignore that section. We don't care about that. Okay? Now, we need some concentration, some things to plug in here. So let's think about what's going on. We already know how much of our chemical CH3NH3 has been made, right? We know that because on the last slide we calculated our moles of acid and our moles of base that reacted. Okay, we found that 0.114 moles of acid and moles of base reacted. So equal moles of acid and base. Well, it's all a 1-to-1 ratio. So if those reacted that much, they're going to produce the same amount of product. So that's how many moles of our product we've made. Now, it's now in a new solution. We've added 35 milliliters to, we calculated on the last slide, 42.9 milliliters. So we now have a new total volume, which is 77.9 milliliters, or 0.0779 liters. So we can find the molarity of that solution. So 0.0114 divided by 0.0779. 0.146 molar. All right, so that is our initial concentration of our product there. And then it's going to react to form these, but they start as 0. Now, we don't know how much is reacting. We're going to use X, 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 and we bring it down. So 0.146 minus X. Okay, so we find, first we write our reaction. So our conjugate, our product, plus water, what does it make? And let me just point one other thing out. So CH3NH3 plus, we had a base, the initial chemical. So I'm gonna erase and start over. So this initial chemical was a base. It formed a conjugate acid. So now this is an acid, so it's gonna act like an acid and give away a hydrogen to water. So that's how we know what we're making in the products. Okay, acids always give away. Okay, now we want to solve for X, right? We've done that before with rice tables. Well, if we want to solve for X, we need a K value to plug in. We can write an equilibrium expression. So this is our Ka because it's our acid reacting. We would have the product CH3NH2 times H3O plus or H plus over our reactant CH3NH3 plus. So that's our expression. Now we don't have a Ka value. If we look up here, we have a Kb value, but we can switch between those two. I'm going to do that over as a side calculation. Remember that Ka times Kb gives us Kw, the equilibrium constant of water. So when you have a conjugate acid and conjugate base, we can switch between their K values using Kw. So Kw is 1 times 10 to the negative 14th. We have our acid. We would have to divide by, we have our base on our acid. So we're going to divide by Kb on both sides, and that would give us our Ka. So our Kw value is 1 times 10 to the negative 14th divided by our Kb that's given at the top, 5.0 times 10 to the negative 4th. So we get 1 times 10 to the negative 14th divided by 5 times 10 to the negative 4. And we get 2.0 times 10 to the negative 11th. So that's what we want to plug in for Ka. 2.0 times 10 to the negative 11th. That's going to equal, we've got x and x on the top, so x squared over, and our value is very tiny, so we can round this to just 0.146 instead of minus x. So we're going to multiply 2 times 10 to the negative 11th by 0.146. We get 2.92 times 10 to the negative 12. I think our bell's going to ring in a second, so ignore that. That equals x squared. And then, of course, we want to square root both sides. And so x is going to equal the square root of that value. And, messed up my calculation here. Okay. So the square root of our answer. Clicked the right buttons that time. And we get 1.7 times 10 to the negative 6th. And that is our x value. Now remember, we're not done. Our whole goal here is to figure out the pH of the solution at the endpoint. But x gives us our concentration of our H3O plus, which is the same as our concentration of hydrogen. So to find pH, we're going to do the negative log of that value. So negative log of 1.7 times 10 to the negative 6th. And we get a pH of 5.77. And that is our final answer. So it is convoluted. It is a longer process, but it's not impossible, and it's just taking a lot of steps we've done before and putting them together a little bit. The new part is having to write that reaction for that new equilibrium forming. And if we look at this, if we think about our pH, we've got a strong acid and a weak base. So our ending pH should be towards the acidic side. So it should be, I knew that was going to ring. So it should be more acidic, and our final pH is 5.77, so it's on the more acidic side. All right. We're going to do another example of this to see what's going on with our with another reaction, since it's a little more involved. So we've got 25 milliliters of a 0.1 molar HCHO2 solution. So we've got our pKa value. We can always find the Ka from that by doing 10 to the negative pKa. So we can do that as a little side calculation in a little bit. So that acid is titrated with 0.8 molar sodium hydroxide. We want to find the volume of sodium hydroxide used to titrate it. Let's just start with that part. So that's when we want to do our volume times molarity of our acid equals volume times molarity of our base. Okay, so our acid, we can tell sodium hydroxide is, I got that OH, that's going to be our base. So we're going to plug in our acid. We've got 25.0 milliliters times 0.1 molar equals volume of our base times the molarity of our base, 0.8 molar. So to get our volume of our base, we're going to divide by our 0.8. Molarities are going to cancel, and we're going to get 25 times 0.1 divided by 0.8, and we get 3.13. We got 3 sig figs here. Milliliters, this is our units left, is equal to our volume of our base. So that's how much base it took to reach our equivalence point. Okay, so where our moles are equal to each other. Now that's actually another key thing that I like to go ahead and calculate, is how many moles of each chemical did we have at that equivalence point, because that can come in handy as we do other calculations. So let's just do that as a little side calculation. If I want to find out the moles of my acid or the moles of my base, they're going to be equal, so you can just pick one. We want to do the volume in liters times our molarity. So moles are going to be equal to liters times molarity. So let's just do our acid, 0.0250 liters times 0.1 molar. So our moles of our acid, 0.025 times 0.1, is going to give us 0.0025 moles, in this case, of our acid. Okay, so that's, and that would also be our moles of our base, right? Because they're equal at equilibrium. That's what that this calculation up here tells us. Okay, so it's just handy to have, so we know how many moles are reacting. Now, we want to also calculate the pH at the end point of the reaction. So to think about that, we want to think about what the reaction is that's occurring, and then go from there. So our reaction that's occurring, we've got HCHO2, an acid, plus a base, NaOH. So our base, our OH, and our hydrogen are going to form water. And then we're going to get our salts. So sodium plus the rest of our acid, CHO2. Now, we could go ahead and do the net ionic equation from this. Our acid is not on our list of strong acids, so this is going to be weak, so it stays together. Our base is a group 1 metal, so it separates. Water stays together, and then we've got our salt, which will separate because of that sodium ion. And then we can go ahead and get rid of our spectators, which would be our sodium ions. So the reaction that's occurring in our container is our weak acid plus hydroxide making water, and our conjugate base ion. Okay, now because this is a weak acid and it forms its conjugate base, we're going to have an extra equilibrium happen. Okay, when it's just a strong acid, strong base, they react, we form water and salt, and everything's fine. But when we have a weak acid, our conjugate base is going to do another side reaction. So we're going to take our conjugate base, and it's going to react with water. Oops. Now, if that's a conjugate base and it's reacting with water, water will be the acid and give up hydrogen and become OH. And then the other chemical will gain the hydrogen and become its acid form. So this reaction starts to occur, and we want to know what the concentration is at equilibrium of our hydrogen or hydroxide, in this case our hydroxide ion, so that we can find pH. So we need this number. Well, we got to plug some stuff in. So firstly, we need a concentration of this product up here from our reaction. So if our reaction goes to completion, we have a 1-to-1 ratio of reactants to products. So the amount of moles of acid and base that react is equal to the moles of product that we make. So over here, this little side calculation I already did gives us our moles of acid and base, but it also gives us our moles of that product, which is that CHO2 minus. But we need a molarity, right? We're plugging into a rice table, so we need a molarity. We got to divide it by the liters. But this is the liters of the whole solution, everything added together, a new total volume, because everything's mixed now. So we have 25 milliliters of our acid, and then we've got this volume we calculated up here, the 3.13. So 25 plus 3.13 is going to give us 28.13, but we got to change that into liters. So 0.02813. So our molarity of that ion is 0.0025 divided by 0.02813. 02813. There we go. So we get a molarity of 0.08. Let's see, we've got 2 sig figs, so it's 0.089 molar. So that is going to be our initial concentration. So that's how much of that conjugate base we're starting with, and we want to know what's going to happen to this equilibrium. Well, we're not starting with any other product of this equilibrium. Go ahead and make an equilibrium arrow there. So that means we're going to be adding some amount to this product side. So we're going to be subtracting from the reactant side. So 0.089 minus x and x and x. So we got to solve for x so we can get that hydroxide ion concentration. Then we can get to our pOH and our pH, right? This is a long process. You just got to stick it out. Well, up here, in order to plug our rice table into something, we need a Ka value, we need a Ka expression. So up at the top, we started calculating our Ka value. 10 to the negative 3.74 gives us, let's put this in scientific notation, 1.8 times, let's see, 1.82 times 10 to the negative 4. That's our Ka value. So then we need a Ka expression. So it'd be products over reactants. We'd have the OH and the HO2 on the top. So let's go ahead and plug it into the K expression. 1.82 times 10 to the negative 4 equals our products. So we got x, and x would give us x squared over our reactants. And this is that key part where we get to ignore that x, right? The amount of x is going to be so tiny because of our equilibrium constant that we get to ignore it. So we're just going to round that to 0.089. All right, we want to solve for x, so we're first going to multiply by 0.089. So 1.82 times 10 to the negative fourth. We're going to multiply by 0.089. And we get 1.62 times 10 to the negative 5. And then we are going to square root both sides. So x is going to equal 4.02 times 10 to the negative 3. So that is our x value, which means that's our hydroxide ion concentration. So that equals our OH minus. So that means we can find a POH. So a POH would be the negative log of that value, 4.2 times 10 to the negative 3, negative log. So we get negative log, I put in the wrong number, 4.2, 10 to the negative 3. 2.38 is our POH, and we want the pH. So we're going to do 14 minus 2.38, which would give us 11.62. Okay, whew, that was a lot. But we got to our final number. Okay, this process is a little more tedious. I get it. So let's just talk through it. So we started out finding our volume of our base. So when we reach our equivalence point, so when we have equal moles of acid and base, we can find our volume or any of those missing pieces from that. So we have our volume of our base. I went ahead and found the moles of the acid, in this case, using the volume and molarity, just so we had that. That's going to give us our moles of acid, moles of base that reacted. Okay, went ahead and looked at our reaction, made our net ionic equation so we could see what's going on, and we got a weak acid, so we're going to form its conjugate base. That is going to form its own little equilibrium, which we have to then use to find the pH. This only happens when we have a weak acid or weak base involved. So we take that conjugate, we add it with water to see how it's reacting. It's a base, so it takes a hydrogen from water and becomes the acid form, and we got hydroxide left. Now we want to do a Rice table to figure out what is the equilibrium that's going on here. What's our equilibrium concentration, in this case of hydroxide? So we get our initial amount of the CHO2 minus, that conjugate base, and we do that by taking our amount of moles of it that's formed, because it's a 1-to-1 ratio with our acid and base. We get 1 mole of the product, and dividing it by the new total volume. So we had 25 milliliters plus 3.13, so we had our new total volume. We get our new molarity of that and plug that in. We don't start with any product, so we're going to add to the product side and subtract from the reactants, and then we're going to plug it into our K expression. So it'd be Ka equals x squared over 0.089. All right, so then we can go ahead and solve for x. So we multiply by 0.89, do our square root, we get our x value, that's our concentration of OH. So then we find the POH, so then we can use that to find our pH. Now we can see our pH is at 11.62. So the pH is more basic. And we can check our work and make sure if that makes sense by looking at our reaction. Our acid is weak and our base is strong. It should be, your pH should be closer to the stronger substance. So it should be closer to the basic side, which it is in this case. All right, we got one more quick slide. I know this is a long video. Okay, this just gives us a quick summary. So we have one on our titration curves. So if we have a strong acid and strong base, they're going to have a pH at the equivalence point of 7. So this is our example titration curve. So this would be a strong acid titrated with a weak base. So we start with the acid, we end with the basic. And then for a weak base and strong acid, so if our weak base is what we're starting with, and we'd start high and we're going low, its equivalence point is going to be less than 7 because the acid is stronger, so it's going to shift towards the acid. We can determine the pH at the equivalence point. We use the reaction of the conjugate of the weak base reacting with water, solve for X in our rice table, then find the pOH and the pH. And then similarly, if we have a weak acid and a strong base, just like we saw in the last slide, we're going to do that same type of thing, but we're going to have a pH at the equivalence point that's greater than 7 because we have that strong base. For both of these, we can find our pKa or our pKb. We do that with half of the volume at the equivalence point, or we call that the midpoint here. We do that. So we find the volume at the equivalence point, we call that V. We cut that in half, so half of V. We go up and find the pH at that point, and then that's going to equal our pKa, and that'll be for both of these. So that's a quick overview of how we can use these, so it's a good little reference for you. Like I said, I'm sorry this video is so long, but it's a lot of info, a little bit longer problems. You guys got this.